So in this topic, we'll talk about the conservation of mass. For the conservation of mass, just consider you have some sort of volume. Okay, we're going to call this volume R. And let's suppose we take a small fluid particle here. Okay, then that fluid particle has a small mass dm that will equal to your density times the small volume V. Okay, so and then that small element is what we're going to call a particle. Okay, it's going to be a small particle that we will evaluate and see what happens. So according to the conservation mass, what he says is that your total mass, your delta mass has to, with respect to time, has to be 0. Another way that we write this often is m dot as well. And what we are basically saying is what all the mass that comes in has to equal to, another way of writing it is equal to all the mass that goes out. Okay. But this is only true if my control volume, the mass in my control volume is not changing. Okay, this is only true. Only true then. So what we are basically saying is you have a small particle there, and that particle now is in this control volume, and this control volume could be changing, right? If it could be changing, because remember, in the particle perspective, we are moving the control volume with the particle, right? So that could be changing. If it's not changing, then that's equal to that. So the big question would be, then what is an expression that I can find for, in the most general terms, for my delta m? I know that it's equal to 0. So to do that, let's consider two cases. First, if we are talking about a fluid particle. Okay. For the fluid particle, then what we do is we got this. The total derivative of dm will equal to the total derivative of rho times my d volume, which is going to equal to nothing else than the volume, total derivative of rho times t. This is using the product rule. Total derivative of the volume of dt, and this all has to be 0. Okay, so if we move on now, this expression right here is nothing else than dv rho dt. Sorry, this is total derivative. Then will be plus, and I could do exactly the same thing on this side as I did before. I can take, this is volume. I could take total d volume over t, multiply by the volume here, divide by 1 over the volume here, and this is nothing else than rho times delta v. So I can express the whole expression as dv d rho dt plus rho v dv. Okay, so now what we can do is we can say for a very small delta v, or when that approaches 0, what your expression then becomes is dt plus rho delta v, v is equal to 0. Okay, This is what your small mass expression of delta mass will actually equal to. Okay, so we are saying that actually gives you this. This leads to this expression, and this is the expression that we use. Okay, that's for the particle. Now, without going to a lot of details on how this actually works, you can actually show that for the we can show that for the material system, for the fluid system, what you need to do is you need to just take the derivative of the whole thing. So for the fluid system, what you will do is you will take, this is respect in R, rho times the volume, and set that equal to 0. And you can work out the whole expression for this based on what we did last time. And that will actually lead you to the same answer, basically. Okay, so this is conservation of mass. In general, before we move on, the conservation of mass for a particle can be written as mass in minus mass out is going to equal to the change of the control volume mass. Okay, so this is nothing else than the mass in the final state of your control volume minus mass in the initial state of your control volume. If this is actually equal to 0, because these are the same, then you have your typical net change of your mass. The integral expression of this, you can show that your expression is actually equal to the following. Okay. And this comes from the fact, if you remember, we derived this expression for this, right? And we are setting this to 0 and taking Q equal to 1. Okay, so that's how we got this expression. So this expression will be the equivalent expression for this expression that we got here. For this expression that we got here, the both expressions are completely equivalent to each other. So this will be conservation of mass. This will be conservation of mass, and what we're going to do is in the next lecture, do a couple of examples to better understand how all these equations actually work.